This video is going to focus on carboxylic acids and chemistry that they participate in. By the end of this lecture, you should be able to say, I can explain which oxygen lone pair is most basic in a carboxylic acid and why. I can predict the relative acidity of a set of structurally related carboxylic acid derivatives, draw a mechanism for the synthesis of carboxylic acids from Grignard reagents, a mechanism for the reduction of carboxylic acids, and a mechanism for the Fischer esterification. I can propose a synthesis that allows selective reaction of ketones in the presence of carboxylic acids and vice versa. I can draw a mechanism for conversion of acids to acid chlorides and for the thermal decarboxylation of beta-carbonyl substituted carboxylic acids. And I can explain the conformational requirements for thermal decarboxylation of beta-carbonyl substituted carboxylic acids. A carboxylic acid has the structure shown here at the top, and it can be written in a few different ways. We need to think about the reactivity of the oxygen lone pairs. Specifically, we need to determine which oxygen is more basic. So if we look at these two oxygens in the electrostatic potential map that I've shown down here, you can see that the carbonyl carbon has this very large red area, and red means more negatively charged, whereas the oxygen in the OH bond part of the carboxylic acid has actually only this very small amount of red in it. And so you can see that the lone pairs up here are actually significantly more basic than those of the other oxygen. Of course, you don't always have a electrostatic potential map handy, and so it's good to think about other ways that you could determine the answer to this question. So first, let's look at a resonance picture of the carboxylic acid. So this is the most representative structure, the neutral form. We can push electrons from this pi bond up onto oxygen because the dipole moment it points toward oxygen, the more electronegative element. So now we have the charge separated picture, and we can also stabilize the positive charge here by donating the electron pair from this oxygen in to form a double bond. So now let's take a look at the oxygen atoms in this picture. Okay. Our red oxygen is negatively charged in two of these structures, and it's neutral in one of the structures. The other oxygen is neutral in two structures and positively charged in the third. So you can see that overall, if we're just looking at the resonance picture, you would predict that this upper oxygen, the oxygen of the carbonyl, is significantly more electron rich, and that's going to make it more basic. Another way to interpret this is that the carbonyl has a significant inductive withdrawing effect, and it's going to actually pull electron density away from this oxygen atom through the sigma bond. And so that's going to make the top oxygen more negative and the other oxygen more positive, or really less negative. Also take note of the ability of carboxylic acids to form hydrogen bonds. So they're actually perfectly poised to hydrogen bond in pairs or dimers as shown here. So the more negative oxygen here is going to interact with the positively charged or delta positively charged H, and same on the other position. So next we'll take a look at the relative acidity of a series of carboxylic acids. So first of all, acetic acid, which has 3 CH bonds on this substituent, but I'm only going to draw one of them out for comparison. And then we can add another substituent here, the chlorine. This chlorine has a dipole moment that points toward the chlorine, so it's going to be delta minus on chlorine and delta plus on this carbon. If you look up the electronegativities of carbon and hydrogen, you'll note that the dipole moment is actually ever so slightly in the opposite direction on this side. And so we have actually an inductively donating methyl group here, whereas here we have an inductively withdrawing chlorine. So when the chlorine atom is withdrawing electron density from this bond, it makes the carbonyl carbon more delta plus, which pulls electron density also out of this oxygen and makes the oxygen have a weaker bond to this hydrogen here, and that makes that more acidic. And then the effect is simply magnified when you add additional chlorines. So now you have two delta minus groups, a bigger delta plus here, so that's going to be more acidic still. And similarly, the trichloroacetic acid is the most acidic with 3 delta minus, a relatively large delta plus, and then a very acidic OH. So a question that'll come up a lot is, which carboxylic acid is more acidic and why? So we'll take a look here at these two carboxylic acids. So on the left we have lactic acid, which builds up in your muscles when you're exercising, and we have propanoic acid. So we just want to take a look at what's different in the molecule first. So you can see that lactic acid has an extra hydroxyl group. So if we draw out what we're comparing that to, that's going to be a CH bond here. So in this CH bond, we have a slight tiny delta minus there and a slight tiny delta plus here. And then in the OH, we actually have a significant delta minus here and a significant delta plus here. So here we have the OH pulling electron density away, and that's going to actually cause an inductively withdrawing effect that makes this carbon more delta plus. That's going to pull electron density away from here and make this more acidic. In the next example, we have benzoic acid and paranitrobenzoic acid. So you can take a look at the resonance structures for those, but hopefully you remember that a nitro group is a withdrawing group. We can draw that out to see why. So you see we have a formal positive charge on nitrogen here, and this oxygen would really like to take these electrons. When that happens, this one here will donate them in, and that'll give us another resonance structure that looks almost exactly the same. And now we can satisfy both of these oxygens. Actually, we can let them each have their minus charge if we then start pulling electron density from the ring to stabilize this nitrogen with the formal positive charge. As we follow that process around, we see that we're going to develop a positive charge here next to our carbonyl carbon. Okay, and you saw the effect up here when we just had a delta plus next to the carbonyl, how that significantly increased the acidity or decreased the pKa of this hydrogen. And now we have a different kind of significant positive charge here that's again going to pull electron density through this sigma bond, and that in turn will pull through this sigma bond, making this oxygen much less electron rich and less able to continue holding on to its hydrogen atom. So this paranitrobenzoic acid will be significantly more acidic than benzoic acid. We can use the pH to tell us about the equilibrium position between the protonated carboxylic acid and the deprotonated carboxylic acid. For this, you'll need to remember the Henderson-Hasselbalch equation. So if you look at the Henderson-Hasselbalch equation, you can see that the pH is related to the pKa plus the log of the concentration of base over the concentration of acid. Remember that when the concentration of base and concentration of acid are equal, as shown in the center here, then you're going to have log of 1, which is equal to 0, and that's when the pH is equal to the pKa. So as we lower the pH, we're going to see more and more protonation of our carboxylic acid, and the predominant species will be the carboxylic acid when the pH gets significantly lower, 2 or less. Conversely, if you start with the pH equal to the pKa and the acid and base have equal concentrations, as you raise the pH, you're going to be deprotonating here, and you're going to lead to a situation where the carboxylic acid is the predominant species. And for typical carboxylic acids, this will be at a pH of 7 or higher. So next we'll take a look at some reactions of carboxylic acids. The first and most simple of these is a reaction with bases. Often you'll see carboxylic acids reacting with hydroxide, bicarbonate, and carbonate salts. So let's take a look here. So if we react with sodium hydroxide, we'll start by using the lone pair, one of the lone pairs on oxygen. We can just draw that deprotonation, and that's going to lead to the carboxylate. That's a term you need to know. Remember, 8 is an ending we use when we have something with a negative charge, and we'll also generate another molecule of water. Next, we'll look at a reaction with bicarbonate. So something interesting happens here that you're probably all pretty familiar with. We have vinegar, and when we add baking soda, so you already know how to form some carboxylic acids from aldehydes and ketones using the pinic oxidation, the nitric acid oxidation, or the chromic acid oxidation. But they can also be formed from Grignards, which is pretty exciting. So you can form your Grignard reagent here in your flask, and then over here there's crushed dry ice, and as that warms up, CO2 will bubble up through this tube, down through this needle, and into this solution, where the Grignard will react with it. And so that mechanism is actually pretty straightforward if you just focus on one side as kind of looking like an aldehyde or ketone. So that gives you the O- shown here. And now when we add a strong acid to that, we will protonate our carboxylate to get to the carboxylic acid. Your HCl is probably going to be an aqueous solution, so it's best if you draw this as a protonation of H3O+, or deprotonation of H3O+, a protonation of your carboxylate, as shown here. You're already familiar with how lithium aluminum hydride functions as a reductant of carbonyl compounds, but an important note for carboxylic acids is that the first equivalent of any hydride source that you add, such as sodium hydride or sodium borohydride or lithium aluminum hydride, the first equivalent is actually just going to deprotonate the carboxylic acid to give the carboxylate. From here, the alene can go on to deliver hydride to the carboxylic acid's carbonyl carbon, or the carboxylate's carbonyl carbon. This intermediate will lead to the reformation of an aldehyde, a reformation of a carbonyl to give an aldehyde, and then another H- will be delivered. And so at the end of the reaction, you end up with a whole bunch of lithium aluminate salts that are quite annoying to deal with. And so there's been a range of specialized workups developed to break up those aggregates and allow you to get your product alcohols out. Probably the most popular of these is the Feezer and Feezer workup. You don't have to memorize this name. You can just write workup, and that's going to give the alcohol as the final product. So as you can see, you're not going to be able to reduce a ketone or an aldehyde in the presence of a carboxylic acid using something like lithium aluminum hydride. However, you can do it through heterogeneous hydrogenation or using sodium borohydride. For heterogeneous hydrogenation, this is typically done with a platinum catalyst and high pressure, at least 2 atmospheres. You can also access the alcohol using sodium borohydride and methanol. We don't want to directly treat with lithium aluminum hydride because that's going to give us the diol. Unless you want the diol, then of course that's a fine way. And if you want to reduce the carboxylic acid and not the ketone, then you would need to protect the ketone, ideally as a cyclic acetal, as that's the protecting group you know best. So now you can do that LAH reduction. This is usually done in tetrahydrofuran, THF as the solvent. That'll give you a primary alcohol here, which if that's the product you want, then that's great, you're all done. If you wanted the aldehyde, then you would go ahead and oxidize that with PCC or PDC or the Swern reaction if you learned that. And then you could deprotect the ketal. To give you a ketoaldehyde. Or deprotect the ketal to give you the keto alcohol up here. The next reaction of a carboxylic acid that we'll talk about is the Fischer esterification. This is essentially the same mechanism as you learned for adding an alcohol to an aldehyde or ketone to form hemiacetal. But when we get to that sort of hemiacetal phase, we're going to go ahead and kick out water rather than continuing on to the acetal. So let's just take it step by step and see what we already know. So first we need to generate H3O+. Then we're going to protonate our carboxylic acid using the more basic lone pair. Make sure you're paying attention there to which one you protonate. So now we've activated our carbonyl to make it a better electrophile so that we can use the poor nucleophile, or let's just say the weak nucleophile, ethanol, to attack. This should look pretty familiar to you. So we need to deprotonate that position to get to this intermediate, and this looks just like our old friend the hydrate, and we want to reform the carbonyl, so we're going to need to kick out one of these functional groups. If we protonate this O-ethyl and kick it out, we're going to go back this way. That does happen. This reaction is in equilibrium, but to go forward in the mechanism, we need to protonate one of these two hydroxyls. They're equivalent, so you can just choose whichever one is handy for you. And do that deprotonation. That gives this intermediate, and now we can reform our carbonyl while we kick out our water leaving group. And now we can use that water to deprotonate and form our final product, which is the ethyl ester, in this case ethyl acetate. So there's a little mnemonic to help you remember the steps in the mechanism. when you see acid, you want to do AAA. So we're going to activate, then we add, then we adjust our protons, then we're going to kick out our leaving group, and again adjust. But the key things to remember are the activate, add, adjust. That'll get you going far enough, and then you just need to remember, how can I reform the carbonyl? And that's by protonating the OH and kicking it out. We can also methylate carboxylic acids by reacting carboxylic acids with diazomethane. We already talked about this in chapter 15, so I'll just review the mechanism here quickly. So first we're going to need to draw out the resonance structures of the diazomethane. Start with the lineup of the atoms, and then you can populate the electrons. It's always easiest to start with the form where you have 2 pi bonds. That tells you this nitrogen is plus, and this one must be the one that's minus. Now we can form the other resonance structure by pushing a pair of electrons over to make a triple bond, and pushing one of this pair of pi electrons over to make an anion on carbon. This anion is then going to deprotonate our carboxylic acid to give the carboxylate. Simultaneously, we've made an ultra-reactive electrophile here. This is like the souped up methyl iodide. And so our oxygen anion here is going to kick out this N2 to form the methyl ester and release molecular nitrogen, which, remember, is a gas, and that's the driving force. We can also convert carboxylic acids to carboxylic acid chlorides, which is a handy reaction and shows up a lot in syntheses. So here we're going to do that with thionyl chloride, and this mechanism is similar to that for the conversion of alcohols to alkyl chlorides with SOCl2. So let's just remind ourselves of the resonance structures of thionyl chloride. So looking at the resonance form, we can see that the lone pair on oxygen is going to be our key basic species. We're going to use that to deprotonate the OH bond. And now our carboxylate can come in and attack sulfur and kick out a chloride. The chloride can add to the carbonyl, push those electrons up onto the oxygen, and now we'll kick out this leaving group. That'll give us our target acid chloride, and this byproduct, which will decompose into SO2 and HCl. So now we're going to learn about a new functional group called a beta keto acid. So if you look at the carboxylic acid highlighted here with this yellow block, if we go one position over from the carbonyl, that's the alpha position. The second position over is beta. So in the beta position relative to the carbonyl carbon, we have a ketone. So it's a beta keto carboxylic acid. And for short, we just say beta keto acid. A cool feature of beta keto acids is that when you warm them up, they can actually undergo a decarboxylation reaction through an intramolecular deprotonation event, which I'll show you here. So first we have to rotate about this sigma bond here to get to this conformation, and then the lone pair on this carbonyl can deprotonate. That'll come down and form a CO double bond. Simultaneously, this carbon-carbon bond breaks, and we give electrons back to oxygen. You'll recognize that you've now formed an enol, and so that has to undergo a tautomerization reaction to form acetone. And it'll actually use another enol as its proton source to do that process. This cyclic reaction can actually also be drawn with one fewer arrow, and I'll show that here. And this resembles kind of like a pericyclic reaction. The top picture is more accurate, but I'll accept either one. So here's a sample problem. To be able to predict the product, we need to first identify which carboxylic acid is beta to the one ketone shown here. So we'll go ahead and label those. If we use the ketone as our reference carbon, then the position alpha to that is here or here, and then beta would be the next one. And so you can see that one carboxylic acid is alpha, one is beta, and the third is actually gamma. So we can only do the decarboxylation for the beta keto acid. And then to do this reaction, we need to rearrange our starting material so that these atoms are in this cyclic transition state. So I've done that here by rotating about the bond indicated here. And now I'll go ahead and draw the overall mechanism for the decarboxylation. Here we have so many proton sources that we don't need to use another enol like we did up here. We can use one of these carboxylic acids to protonate this carbon, and then the resulting carboxylate can deprotonate the H+ to give the final product. This process can also occur with dioic acids, which is a, in this case, a beta carboxylic acid, which is why we don't call it that. We say a beta dioic acid. And the decarboxylation mechanism is the same, only you're going to use one of the oxygens, here the yellow one, to induce the decarboxylation of the other acid. So pause the video and give this a try on your own before hitting play to see me work the answer. So here's the starting material lined up for the reaction. We can deprotonate, decarboxylate, we form our enol. And then we use another of these enols to tautomerize to form the product.